Hello, my name is Tomasz Idziaszek, and in this video I will talk about the solution to the Matrix Challenge 2021 powered by Codility. In this challenge we are given a matrix of size n times n, and every cell of the matrix is colored either black or white. The coloring is given in the form of a histogram. That means in every column some number of bottom cells are colored black and the other cells are colored white. Our task is to find the side of the biggest black square that can be found in this picture. The histogram is represented by the matrix A of size n. The cells of this matrix denotes how many black cells we have in every column. So in this example, in the first column we have only one black square, in the second two black squares, then 5, then 3, 1, and again 3. So everything else is white. So when trying to fit a square inside this histogram, for sure we can fit a square of size 1 anywhere in the histogram. But we can see that we can also fit a square of size 2, but not a square of size 3. So the answer here will be 2. This is the biggest square we can fit. So how to approach this problem? One of the methods that works very well for various problems is to try and simplify the given problem a little bit. For instance, here we are asked what is the maximal square that can be fit into a histogram. So instead of solving this problem, let's say that somebody told us that he or she wants to fit a square of size 2 inside a histogram. And now our task is to determine whether this is possible or not. How would we do that? Well, we need to investigate what are the essential properties of the array that allows us to fit a square of size 2. First of all, we can observe that if a square can be put into a histogram, it could be put in such a way that the bottom side of the square is at the bottom side of the matrix. Next, let's consider all the columns in which this square is located. Since this square is of size 2, each of these columns must have at least 2 black squares. So the numbers in this part of the array A must be at least 2. Moreover, because not only the height of the square is equal to 2, but also its width, we need to find 2 consecutive columns which satisfy this property. In general, if we want to find a square of size k, we need to find a consecutive set of k columns Each column is of height at least k. In order to find this set of columns, we will go through the array A from left to right. We will start at the beginning with a pointer I, and we will move further to the right, and every time we see a column which is at least of height 2, we will advance another pointer j. So first we will advance pointer 1 column to the right, and then we will see that this column is no longer of height at least 2, so we will not advance it anymore. And now we know that we have j minus a columns which satisfy our property. So if j minus I is at least k, then we can say that we have found a place to put a square of size k. Since this length is smaller than 2, we need to iterate further. So we put our pointer I where the pointer j was located before, and then we try to find another set of columns, and here we see that even the first column is smaller than 2, so definitely this column will be bad. So once again we put the pointer I further, and now we can see that this column is okay, because 3 is greater than 2. And then we can move pointer j 4 column to the right. And we have found a set of 4 columns which are of good size. Since 4 is greater than 2, we can say that we have found a place to put a square of size 2. And for instance, it can be put here. Okay, so we have a procedure that allows us to test whether a square of certain size can be fit inside a histogram. Because we have iterated exactly once through the array A, this procedure has time complexity of O of n. It turns out that it's not very hard to expand this idea to the solution to the whole problem, because we can just test out every possible size of the square. We have n possible candidates, so the whole solution will work in time n squared. So now let's implement this solution. First, we will implement the function which verify whether there's a square of size k in the array A. So we will make a pointer I, and we will iterate it until we hit the end of the array. And then we will make another pointer j, and we'll start from A, and we will iterate it until we hit the length of the array, and until the size of the column j is at least equal to k. Okay, so after this while loop, we know that the range from I to j minus 1 is okay. It contains only columns that are of size at least k. So if the length of this range, so j minus 1, is greater than k, we can just return true. We have found the array. Else we need to iterate further. So we need to increase the value of pointer I, and either we have found a non-empty range before, so we can just put j as a new value of I, or we have found a 0 range, and then we need to increase I by 1. All right, and if we end up this loop without finding any set of columns of size at least k, then we just return false. All right, and the main solution will just pass through every possible size from n to 1, and if we verify that this size is okay, then we just return this size. We definitely know that this function will end, because definitely verify with k equals to 1 will return true. All right, so we can run our program. Okay, there's no variable n. So this program is correct, but unfortunately the n, so the length of the array A, can be up to 100,000. So the solution of time complexity n squared will not pass in time. So we won't get perfect score for performance. So how to speed up this solution? Let's look at the return values of the function verify for different sizes of squares. Let's use the histogram on the right for this. So as we say before, in every histogram, the square of size 1 will be fit. So here we have OK. Here we also can find the square of size 2. But for instance, the square of size 6 will be definitely too big. So here we will have answer no. If we try every possible size, we will see that 3 is OK and 4 and 5 are not OK. In this particular example, we will see that there are some answers yes that are in the prefix of this array, and the other answers are no. And this is not a coincidence. Why? Well, because if we know that some square of size, let's say of size 3, can be fit into the histogram, then we know that all the squares which are smaller can be also fit. And vice versa. If we know that some square, let's say square of size 4, cannot be fit into the histogram, that all the bigger squares cannot also be fit. So in general case, we can partition our array of answers into two parts, and in the left part we will have all the answers yes, and in the right part we will have all the answers no. And our task is to find the rightmost answer yes, so this one. So in this kind of setup, instead of going through every possible answer and verifying it, we can do a binary search to speed up the search. And this works as follows. At the beginning, we know that the answer may lay somewhere between 1 and n. Then we will run the function verify in the middle of this range. So let's say in n². And here we will have two cases. Either this function returns yes, and then we will know that all of the smaller squares are also possible. Then we know that the range in which we need to find the answer is now limited to the range n² to n. In the second case, this function returns null, and then we know that all of the bigger squares are also not possible. So the range of the possible answers is limited to 1 and n² minus 1. So this operation halves the size of the range of possible answers. So if we do this thing recursively, we know that after logarithmic number of operations, so the logarithmic number of calls to the function verify, we know that our range will reduce to only 1 point, and this will be the answer. So the overall complexity of this solution will be n log n. One technical issue with the binary search algorithm is to decide which middle element to choose when the range is of even length, especially when the range is of length 2. And since in case of the positive answer we include this element in the smaller range, we need to make sure that this is the right middle element, otherwise we would get an infinite loop. Okay, so let's improve our implementation with the binary search. The verify function will not change. We only need to replace the main code. So I will write two variables for lower bound and upper bound of the range in which we are finding the answer. And while lower bound is smaller than upper bounds on this range is of size at least 2, we will find the middle point, and this is lower bound plus upper bound plus 1 divided by 2. I add 1 because of this technical thing with the ranges of length even. And if we verify that the square of size mid can be fit inside the histogram, then we know that lower bound can be replaced by mid, and else we know that upper bound must be replaced by mid minus 1. And at the end of this loop, lower bound will be equal to upper bound, and this will be our answer. And let's run the tests. They are correct, and if we submit this solution, we will get a perfect score both for correctness and for performance. Although our n-log-n solution got a full score in this challenge, it is not the best possible algorithm for this problem. In fact, we can solve it in optimal ON time. The idea behind this solution is as follows. Instead of finding maximal squares in the histogram, we will try to find maximal rectangles. Why is it useful? Well, let's consider some square inside the histogram, and let's extend the sides of this square to form a rectangle consisting of only black squares. So for instance, we could extend left side here, top side here, and also right side here. So idea is to create a rectangle which cannot be extended anymore. So every side of the rectangle touches the boundary of the matrix or some white cell. Since we are considering only squares that touch the lower side, the rectangle will also touch the lower side of the matrix. So every square can be extended in one or more ways into some maximal rectangle. So in order to find the maximal square, we can find all the maximal rectangles, and in every maximal rectangle we will try to fit as big square as possible. That's pretty easy. If we have a maximal rectangle of size w times h, we know that we can fit here a square of size minimum of w and h. So let's try to characterize our maximal rectangle. First, observe that since the top side cannot be extended anymore, there's a column which has the height equal to the height of this rectangle. Therefore, we will have only linear number of candidates for maximal rectangles because we can fix a column and then try to create maximal rectangle which contains this column, and also the height of this rectangle is the height of this column. So now we only need to extend this rectangle to the left and to the right. So how far can we do this? Well, we need to find the first column to the left, which is smaller than the size of the rectangle. So we need to find this position 1. And also we need to find the first column to the right, which is smaller than 3, the size of the height of the rectangle. So we will find here 2. So if we know the positions of these columns, I and j, the width of this rectangle is equal to j minus I minus 1. So now our problem reduces to the following one. For every position I, find such biggest position j smaller than y, such that the height in position j is smaller than the height in position I. This will allow us to find the extension of all maximal rectangles to the left. In order to find the extensions to the right, it's easy to apply the same algorithm, but on the sequence A reversed. And of course, we would like to solve this problem in linear time. And the idea for the solution is pretty clever, but quite easy to implement. Before the first column, we would add a sentinel value of -infinity, and then we will proceed the columns from left to right. When we investigate a column, we look at the previous one and see whether it's smaller. If it's smaller, then we know that this is the correct extension. We will denote this extension by this arrow because it will gives us a visual interpretation of this problem. But of course, during the implementation, we will store these pointers in additional array. Okay, we will move to another column. Now we will see column 1, and the preceding column has size 3, which is bigger. So we know that we cannot put an arrow here. Instead, we will go through the arrow of this guy and see whether the element pointed by the arrow is smaller. If it is, then it will be a next candidate. Okay, so we continue further. So we investigate 4. 1 is smaller, so here's the arrow. Then we investigate 3. 4 is not smaller, but going through the arrow from 4, we got 1, it's smaller. Now we got 5, smaller 3. Now we get 4. 5 is bigger, but 3 is smaller. Now we got 2. 4 is bigger, so we go through this arrow. We end up in 3, which is also bigger, so we go through another arrow. And 1 is smaller, so this will be the good answer for 2. And finally, for this 3, we got answer 2. So first of all, why is this algorithm correct? So why we can't jump over many candidates at once during the jumps with the arrows? So let's suppose that here we have another column 1, and we know that 3 is bigger, so we will jump with this arrow, and also 2 is bigger, then we will jump through all this arrow here. So why we can jump over all of these candidates at once? Why do we know that these are not good answers for the column 1? Well, we know that these were not good answers for the column 2. So these guys were not smaller than 2, then they will be definitely not smaller than 1. So we can just ignore them. And the second thing is, what is the time complexity of this approach? So we can see that for every element, we create exactly 1 arrow. And since we can see at the picture that these arrows do not cross, so with every arrow, we will jump exactly once. So the total sum of all the jumpings will be linear in the size of array A. So that concludes the linear time algorithm for solving the matrix challenge powered by Codility.